All right, we are in 8.3, lesson 2, lesson dos. And if you thought z-scores or z things were hard, we're going to learn something new today. It's called the t-distribution, and we're going to have t-scores and all that kind of good stuff. Just perfect. All right, having some tea and crumpets. All right, odds are, guys, and I talked about this last section, if we don't know what the true population is, right, if we don't know what the mean is, we probably don't know what our standard deviation is, right? I mean, just throwing that out there. I mean, confidence intervals are all about saying, hey, I'm pretty sure the mean is somewhere within this interval, right? I'm pretty sure it's within that interval. Odds are you don't know what your standard deviation is either for the population, right? I mean, that's pretty silly. You might say, almost never will we know the standard deviation. Because, in fact, to find standard deviation, you actually need to know the population mean. And if I don't know the population mean, it just starts a domino effect. So, most likely, if we don't know this, I don't know this, okay? That causes a problem, right? Because my standard deviation formula is this over this, right? So, when I have to erase, and I say, I don't know what that is, but you know what I do know? I probably do know my sample deviation. Is that going to be 100% accurate, though? Maybe not, right? Because it's just a sample. My sample standard deviation might be a little off, right? It's not going to be exact. So whenever we have to use our S, we call it a t-distribution. Okay? Does that make sense? All right? Hopefully. So notice here's the two differences down here. Okay? Z-distribution is when I actually know my standard deviation, which is very rare. I've seen like 1 or 2 problems on the ACT where you actually know the population deviation. Most always, we don't know the actual standard deviation. We have to use just the amount that we found out from our sample. And so we have to use S. That is when I use T. Okay? Now, to understand this, when we're dealing with proportions, will we ever have to have a t-score? No, because we never have to know our standard deviation. We actually know the standard deviation is this formula, which, you know, we don't have to have a standard deviation to figure this out because all we need is the percent, right? So we will never, ever, 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 ever have to use a t-distribution for percentage problems. Okay? Percentage problems, we don't ever have to worry about deviations, or standard deviations, whatever, because we can actually find the actual amount by using our data. All right? So, the only time we have to worry about t-distributions is when we're dealing with means. Now, I'm working on a little spreadsheet that has a little tree diagram and shows kind of like, when do you use this, when do you not use this. Hopefully, I'll have that to you, maybe even by today. Okay? But, if I don't know the actual standard deviation, I have to give a little bit more wiggle because that's just an approximation standard deviation. So, when I'm doing an actual amount, like I know how far out it will go. But when I'm using a sample standard deviation, it could go out further because that sample standard deviation is not 100% accurate. So I've got to give a little bit more leeway. So the other thing I guess I want to tell you about in statistics is, as a statistician, we need to be very accurate. So we should never guess more than what we should. We should always kind of step back and say, okay, let's give the conservative guess here and be just extra careful, because I would hate to say something that's not true. So I would rather extend an interval than decrease an interval when I'm trying to estimate a population. Okay? So Here is something I know you guys have all been wondering about. Okay, with t-distributions, we use this thing called degrees of freedom. You guys like my Photoshop job? Look at that. Oh man, you get it? Degrees of freedom. Oh boy. All right, and degrees of freedom is always, guys get this, and we label this as df. I don't know why we label it df, but we do. df is always your sample size minus 1. Now this brings up kind of a weird thing. Why don't we just have our df be our sample size? I don't know. I mean, there is some weird math behind it all. But I just wish for simplicity's sake we would just say degrees of freedom is our sample size. But we don't. We always take one less than our sample size. So for instance, you might have noticed when we turned to table B to find out our critical value, right, at the bottom, remember we went all the way down to infinity, you might have noticed that there were df over here, right, degrees of freedom. Okay, that's what df stands for. And when we get all the way down to the bottom, that would give us our z-score. Sometimes most of our charts say infinity down here, meaning we're pretty sure of our standard deviation. So, and at 95% confident, our z-score would be 1.96, right? However, if we take a small sample size and I don't know the actual standard deviation, I need to give a little bit more wiggle. So I'm going to have to go out a little bit more. So notice what happens here. If I only have degrees of freedom of 10, look at being 95% confident, I'm giving even extra. I'm giving a little extra. We're going to be extra careful. We're going to spread it out a little bit more. If I have 11 people, it's getting a little bit smaller. I'm just saying, okay, you know, I've got 11 more. I'm a little bit more careful, right? As you keep increasing your sample size, you become more confident in your standard deviation. And so we can slowly approach the actual z-score of 1.96. Now, I don't know if this is all making sense. I hope it is. If you have questions, please ask me. But remember, our degrees of freedom is always n minus 1. So, suppose you want to construct a 95% confidence interval for a mean based on a simple sample size of n equals 12. All right? Well, if n equals 12, don't go to 12. Degrees of freedom is always n minus 1. So I want to do the 11. And I would go from 11 over here. So this would be my critical value now that I would use. I would give it just an extra little bump and figure that out. All right? Okay? So for instance, I think I have a page here. Yeah, here's what we actually find in here. Here's table B. Here's your degrees of freedom. Right? Okay? So let's say sample size. We're going to play a little game. Sample size is 21. What degrees of freedom am I going to use? I'm going to go to 20, right? All right. And then if I want to be 90% confident, well, 90% confident with the sample size of 20 is 1.725. Now, if I actually knew the standard deviation, the population deviation, I would come right down here, and this is the exact value, right, without any extra little bump. It would be 1.645. But because I don't know the actual population deviation, I would select that. Okay? Let's play again. So this is fun. This is real fun. All right. Let's do sample size of, let's go 100. What if I did a sample size of 100? All right. So I come over here and I say, oh, 100. Oh, but remember, DF is actually 99, right? Okay. Well, there isn't a 99. It goes right in there between 80 and 100. Now, here's where you should get your underwear in a bunch. Because even though we're really close to 100, if we round up to 100, that is decreasing our sample size, and we might not be as accurate. We always want to be conservative as a statistician. So we're not going to round up. We want to round always down, even though it's so stinking close to 100, I'm going to always round it down just to give it a little extra. So my degrees of freedom that I would actually use, and I would say maybe with using a conservative degrees of freedom of 80. So I would actually use that one, and I might state it in the problem too. Now realize this, your calculator actually has all of these in its calculator, so the calculator will actually use whatever you put in there. So calculator actually has degrees of freedom of 99. So just be mindful of that, and maybe you would want to type in a sample size of 81 into your calculator so it'll pump out this, just so they correspond with what you're actually saying. All right, so here we go. Let's do a problem here. Go back to question 1 in your notes. Let's say Mrs. Rudkin was not able to be found to give us the population standard deviation. All right, now remember, I think it was 4.4, right? But obviously, if we asked her what's the population standard deviation, couldn't we just ask her what's the population mean? Right? Okay. She wasn't able to be found, so I don't know that. Get that out of your mind, guys. All right, I believe, oh shoot, let's go back to 1 quick. What was question 1? How many monkeys? Question 1. All right, we got a sample of 18.9 out of 32 students. All right. 18.9 out of 32 students. All right, so mean of 18.9 out of 32 students. All right, okay. So it says, what would be a 95% confidence interval for this? So I'd still do my state plan do conclude. I'm going to do a confidence interval. This time I'm going to do a T confidence interval, though. And you would be able to find that in your calculator. If we have time, maybe I'll show you the T one. It's right below the Z. Then I'm going to just kind of start clicking here. So I'm going to go 18.9. State plan do conclude, remember, still stays the same. My critical value. Now here's the deal, is I don't actually know. I don't know the actual standard deviation. I have to use my sample of 4.1. So I am going to use a T critical value, not a Z critical value, a T critical value. So I want to be 95% confident. So my degrees of freedom will be 31, because that's 1 minus. So I need to go back to that chart and look for degrees of freedom of 31. Oh, they don't have 31. So I got to round down to 30. Okay. And then 95 would be this. So this is my critical value now for 95, meaning it's close to 1.92 or 1.96, but I'm given a little extra wiggle room. So 2.042. Oops. 2.042. Okay, and then my standard deviation, remember I don't know actually the actual amount, so I'm going to use 4.1 divided by the square root of n, which is still 32. Okay. All right, now we could calculate this by hand. We could plug it into our calculator. Let me just show you. I do have enough time, I guess, to show you how to do it in your calculator. And I would go to Stat, over to Tests, and you don't want the Z interval anymore because I don't know the actual standard deviation. I'm going to go down to the T interval. So I'm going to hit T interval, and we have our stats. Our mean was 18.9. Our standard deviation, notice it's an S this time, 4.1. And my sample size was 32. All right. And I'm going to go down to calculate. Right. Boom. Right there. There's the interval. Okay. So I'll write down the interval. So I wrote down the interval, and if you compare that with the one that we did previously, you'll realize it's pretty stinking close together. All right. That's intro to t-scores. We'll work more on lesson 3. Bye.